So quiz, what is today? Today's Monday. Quiz on Wednesday, right. So it's our last quiz. Remember, these quizzes are 25 points each, so they all add up to equal to an exam grade. So the quiz in itself isn't worth that much, but they all add up to count for something. And we're looking, if you're preparing for this, you should look at exams 4, typically. Unless you're looking at fall 15, 16, or 17. And the Chapter 7 questions are all, on those semesters, all in exam 3. So I brought all those exams today, but you can find them, of course, on the website. So exams 4, all the other semesters, I take that back. If I'm looking at fall, I usually only look fall 14 through 20, like when I'm working with students. But that doesn't mean that your quiz questions come from fall 14 through 20. They can come from any exam in there. But I find that, you know, if you look at that 6 or 7 years worth of exams, that's probably enough to get the gist of it. You might not see the exact question, but you'll see something that's really similar. Anyway, so this is fall 14. The first, looks like 6, 7, 8 questions are from Chapter 7, first 8 questions. You can tell because right here we begin looking at moments of inertia and torques and those things. You'll know that that's Chapter 8 because you'll see those topics. This is a good example of what you'll see in your quiz. There'll be a conversion like number 4, calculating the angular velocity of some object. In this case, it's a clock. Some kinematics questions like number 2. Another kinematics question like number 1. You'll probably have a couple kinematics questions. Yeah, this looks a lot like your quiz. Some different conceptual things. This is straight from the concept test for Chapter 7. If you want to study that, you can too. Are there particular questions that you want to look at, Julian? Okay. Is that the centripetal force one? The Ferris wheel. Okay. This is fall 18, number 5. I don't remember if I put this on there, but if I didn't, it'll be something important for the exam. I don't remember if it is or not. I'm not being coy, I just don't remember. All right, so a Ferris wheel is like this, and it spins around, say in this direction. Is that the air conditioner? Certainly not. That must be the heat, right? Is it warm air coming out? Anyway, so I can have 2 scenarios. I can be at the top or at the bottom. So these are just the chairs in the Ferris wheel at the top or bottom. And in both cases, I have forces that are upwards, that's the normal force, and downward, that's the weight. Normal force, weight. And remember the elevator problem that we worked in the semester? You have an object in an elevator. If it's moving up the acceleration, then we can calculate the normal force. You know, it looks a lot the same. That have a normal force and a weight. And it was important what was the direction of the acceleration. Same here. This is almost an identical problem, except your acceleration is coming from something different. That your acceleration is the centripetal acceleration. So in this case, your centripetal acceleration is always towards the center of the circle. That's what centripetal means, center seeking. And so my centripetal acceleration here is in the downward direction, and my centripetal acceleration here is in the upward direction. Depending upon what direction the centripetal acceleration is going to depending on the direction of your centripetal acceleration will impact whether your normal force is bigger or smaller than the weight. Where is it going to be bigger than the weight? At the top or bottom? At the bottom, right. So at the bottom, if your Ferris wheel is going really fast, at the bottom it feels like you're pushed down into your seat. And at the top it feels like you're lifted up out of your seat. Okay, same with the elevator. It's the same effect. So here I'm looking at the lowest point, and I want to know what the normal force is. What I do is just like we did in the elevator problem, is I say the sum of the forces, and the sum of the forces is the normal force, which is upwards, minus the weight, and that's equal to the mass times the acceleration. This acceleration is my centripetal acceleration, and I'm going to go ahead and put a little positive sign right here, just to remind me that that is a positive value. And so then my normal force will equal to the weight plus mv squared over r. So since my weight here, my mass is 100 kilograms, so my weight is 1,000 newtons, I can get rid of this one, and this one, because those are all, oh wait, no, I'm sorry, I can't get rid of all those. I can only get rid of this one and this one. I can get rid of those two because, you know, those are smaller than 1,000 newtons. And I know that my normal force has to be bigger than 1,000 newtons. So now it's a matter of calculating this. Austin? Okay, so let's notice up at the top of the trajectory, let's look at the sum of the forces here. The sum of the forces at the top will be Fn minus Fw is equal to MAC. Hey, Ben. At the top of the trajectory, this centripetal acceleration is negative. And because it's a negative number, if I do this, I get my normal force is equal to Fw minus MAC at the top. And so since the normal force is the weight minus this additional quantity, that means that the normal force is less than the weight. Whereas down here, the normal force would equal to Fw plus MAC, because I have a positive acceleration. What's that? Yeah, not because the weight is greater than the normal force, but because the normal force is equal to the weight plus this additional value, whereas up here, the normal force is equal to the weight minus this additional value. It's just like the elevator problem. If I'm going up, if my acceleration is up, my normal force is bigger than my weight. It feels like I'm being pushed down. If I'm coming down, the normal force is smaller than the weight. It feels like I'm being lifted up, like I'm lighter than I actually am. All right. Elena, can I finish this? Okay. So here, there are some unit conversion things that we have to do in this, and that's where you sort of get in the weeds a bit on these. But you're going to get in the weeds on this exam, so make sure that you're familiar with these, the units and the conversions, and that comes into this problem quite a bit here. Remember that the centripetal force is mv squared over r, but I can also say that it's m omega squared r. How I get that is I just say that v is equal to omega r, and I plug this in for v, and I get this mu expression for centripetal force. That's not on your equation sheet. However, this value for omega has to be in radians per second. It cannot be in revolutions per second or degrees per second. There are 3 or 4 equations, S equals theta r, v equals omega r, a equals alpha r, and a equals v squared over r, or omega squared r. All 3 of these have to be in radians, or in SI units. Radians or radians per second or radians per second squared. You have to have those in the proper SI units whenever you're using those equations. Whereas the kinematics equations, the theta equals omega naught t plus 1/2 alpha t squared, and that omega equals omega naught plus alpha t, like those can be in degrees or radians or revolutions, and you've probably worked through some where you had that. Because whatever units you put in is what you're going to get out. But on these equations, you have to be consistent with your units in SI units. You're never going to go wrong with SI units, so if you ever have any question, just convert it to SI units. But be careful that you're matching the units that are in the answers, that you're converting them back into whatever the answer requests. Okay, so I can find this out. I can finish this. The normal force is equal to the weight. The weight is m times g, that's 1,000 newtons. I just did 100 times g, plus 100 kilograms, that's the mass. I'm going to do omega squared here times r, and the r was 20 meters. Now I need to figure out what omega is. This is a hard problem. This is probably going to be a free response problem, by the way, on your exam. So omega, to find out omega, oh look, I've already given you omega, is 0.1. So it's going to be 1,000 plus 100 times 0.1 squared times 20. And so that's going to be 1,020 is the answer. Elena? Oh, awesome. Okay. Okay. Are we okay with this one? The hard part about this, I mean, there's the whole part about the centripetal acceleration and was the normal force bigger or smaller and figuring out what is the normal force. But then also the hard part is getting all your units straight. That can be difficult. And students will mess that up. Don't let that be you. Okay, you don't have to mess it up. All right. Okay, so I did that conversion for you, but if it wasn't given to you, I would have 1 revolution per minute. And then I would convert my revolutions. 1 revolution is 2 pi radians. And then 1 minute is 60 seconds. And then that's equal to 0.1. You are going to have just a straight up convert this to degrees or radians or whatever, but then you're going to have conversions that you'll have to do embedded within problems. So be prepared for that. Joanne?
What time to divide it by?
Okay. Well, get rid of all this. That's because you don't use an analog clock. So, in a clock, you, what is this? This is 12, 3, 6, 9, right? Y'all know clocks? That's a clock. And so here, if I'm going between noon and 6 p.m., that's from there to there. Well, how many radians is that? That's 180 degrees, which is equivalent to pi radians. I can't really, I mean, you just need to know analog clock. You're probably going to have some variation of a clock problem on there.
That's negative. Sorry, my dear. That's negative, right? Going in that direction?
That would be negative, but I didn't give you a sign, so yeah, you're right. Clockwise is negative. Mm-hmm. Yeah, there are lots of different variations of these. Oh, 4. Huh? Yeah, if you know the unit circle, 0, pi over 2, pi, 3 pi over 2, and 2 pi. Oh, come on, y'all need to know the unit circle. No, the unit circle is really important. Okay, so it'll help you to know the unit circle. But be aware that on the clock that, you're shifting things around because really 0 is at 90 degrees on a clock. Yeah, so what is the angular velocity of the hour hand on a clock as it travels from midnight to 3 a.m.? So I'm going from here down to here. So this is the hour hand. Oh, goodness. So the time for the hour hand to go from midnight to 3 a.m. is 3 hours, right? And then the angular displacement that it undergoes in that time is, what was that, pi over 2? Yeah, pi over 2 radians. Notice that I have seconds here, so I need to convert this hours to seconds. In 1 hour, there are 3,600 seconds. So that's equal to, well, 390, was it 10,800 or whatever? 10,800 or 18,000? Yeah. And so that's in seconds. So now I'm certain that I'm in the right units, because I have radians for my theta and I have seconds for my time, and that matches the units that I have in all my options. So then I just divide the two. I say pi divided by 2 divided by 10,800, and I don't know, that's 3 divided by 21,000. 1 point. Is it C? Is that the right answer? Yeah. Okay. But you know, if it's the second hand, that would just take 15 seconds to go from 0 to that 15-second mark.
Which hand you were talking about.
Yeah, pay attention to what hand I'm talking about. It changes the answer. I'm sorry, is the analog clock, is that too antiquated?
If it went from midnight to 3 o'clock, which was a minute hand, what did you say?
That if it was the minute hand, that would be 15 minutes. If it's the second hand, that would be 15 seconds. Well, I mean, I would ask you that the minute hand from midnight to 3 o'clock, because that would go around a bunch of times, right? But if my minute hand is moving from the 12 to the 3, that's just 15 minutes.
Oh, yeah. Oh.
Y'all get an analog watch and just wear it to class. Maybe I'll put an analog clock up on the screen so y'all can look at it. If I give y'all that question, would that help? Do you want me to do that? Okay. Did you see me roll my eyes? I roll my eyes. My son has a Casio analog watch, but my daughter has an iWatch or whatever. What do you call it? Apple Watch, yes. And she's always thinking she's all better than the rest of us, but really she's not. What do you have? Apple Watch. That's what she has. Yeah, she changes it to an analog watch. No. All right. So what else, y'all?
6 on ball 18.
Uh-huh. It's making me sad that we're not getting a chapter 9. But it makes y'all happy, right? Does it make y'all happy? And that's really what's important, isn't it?
Question regarding that. Are we going to learn stuff and will it be on the final or will the final be just after chapter?
No, we don't do any new content after for exam 4. Okay. All right, a fan spins at 12 revolutions per second. That's the initial velocity. This is Fall 18, Exam 4. So my initial velocity is 12 revolutions per second. And then I turn it off and it starts slowing down. So alpha then is 3 revolutions per second squared. But because it's slowing down, I know it's the opposite direction from omega, so it's negative. You should be doing the same thing, by the way, when you're reading these questions, that you're writing down the things that you know, and you're writing them down with the proper variable names. I've seen students make a lot of mistakes just in writing down. They will say alpha equals 12 and theta equals 3 or something like that, and then that of course messes up their own. You'd be surprised at how many students do that, but they just don't really know how to connect the variables to the names of the quantities and the numbers. So that's sort of the first big hurdle. And then I want to know what is the angular displacement before coming to rest. So I want to know what is theta, and omega final is equal to 0. So usually when we say rest, we're talking about the initial state, but in this case it's switched around, that it's starting out at some speed and then it's slowing down. So I want to know its angular displacement. Well, that I know it's going to be theta equals omega naught t plus 1/2 alpha t squared. And then I like to go through and underline the things that I don't know. I don't know theta. Oh, but shoot, I don't know t either. So, yeah, that's a problem, right? So I need to go and figure out what t is. We've done problems like this before in chapter 2, where I can go and figure out what t is through this. Omega is equal to 12. Oh, excuse me, sorry. Oopsie, I made the same mistake y'all might make. 0 equals 12 plus negative 3 times t. So t then is equal to 4 seconds. By the way, if you do make a mistake and you get these two things switched accidentally, you're just going to get a negative t. And then you'll say, oh, well, time can't be negative. And then you'll go back and you'll say, oh, this was the mistake that I made. Okay, but look out for that. So now I know the time. Now I can figure out my angle theta. Omega naught was 12. Look, I'm just looking back over here. So I see that's 12 times 4 plus 1/2 times -3 times 4 squared. 48 minus 8 times 3 is 24. So it's going to be 24 revolutions. Notice that I didn't have to convert it to SI units. I do not have to convert this to SI units because if I have consistent units in theta, omega naught, and alpha, then it'll stay consistent. As long as I'm using revolutions throughout all, radians throughout all, or degrees throughout all of those quantities, then I'm okay keeping them. And usually on these, you'll see that I have revolutions here and revolutions here. So you don't have to do any unit conversions. It's only when you're dealing with centripetal forces or are doing those, converting your linear to rotational quantities, those 4 equations that I wrote for you earlier. That's when you need to convert to SI units for radians. Okay? Yeah, you missed the negative. Yeah, that's another big thing. So here, if it's slowing down, that's important. That it's starting at some speed, that means it's going to have a negative acceleration as it slows down. Or an acceleration that's opposite the velocity. Okay? What else, folks?
You don't have any like number 2? I know it's 1.1 revolution.
Oh yeah, of course, yes. You will have a conversion, where it's just convert this number of revolutions to degrees or convert it to radians. So don't forget your conversion factors, that 1 revolution is equal to 2 pi radians is equal to 360 degrees. Okay? Let's look at number 4 too. This has to do with centripetal forces. Remember, there were a couple of different variations of problems that we had to do with centripetal forces. This is the situation where I have a car that's going around a curved path, and I want to know what is the maximum safe speed. Remember, on this situation where I have a flat road, the flat road is important because if it's banked, you have other things that are providing the centripetal forces. On this quiz, you will not see any banked curves. I think there are a few questions buried in some of those exams where it's a similar question, but it's banked, right? Like, you know what I'm talking about? Banked at an angle, but you won't see that. So for now, at least, you can put that to the side, but it might come back for the exam, and I'll let you know if that's the case. All right, so here, though, on a flat road, the only centripetal force is the static friction. The static friction is the centripetal force. Now we know that the static friction is mu times the normal force, and we know that the centripetal force is mv squared over r. Right? We know this. And the normal force is mu mg. The normal force is equal to the weight, and that's mv squared over r. So I can get rid of the masses here. Fortunately, those cancel out. That you see those safe speeds on the road, it doesn't depend upon the weight of your vehicle, the mass of your vehicle. So big trucks need to travel the same speed as small trucks. And then I'd solve here. In this case, I'm looking for v, so I'd solve for v. Okay? And it is what it is. I don't know. All the numbers are there. 0.7 times 10 times 50. And this is, what is it? 19. All right, so I'll just do it. Assuming Elena's right. I'm sure she is.
Why do you have to set it equal to the friction and the,
Yeah, so the centripetal force, we didn't really skip a step, but what we did here is we said that the sum of the forces equals mass times acceleration. And the sum of the forces, there's only one force acting, and that is the static frictional force. And I set it equal to the mass times the acceleration, which is this step right here. So I'm not really doing anything different from saying the sum of the forces equals ma. The sum of the forces is, or the sum of the force, there's only one force, is the static frictional force, and that frictional force acts as the centripetal force. Remember, the centripetal force is not a separate force. It's just a term that we use to describe the center-seeking force when we have an object that's moving in a circular path. Because if I have a an object moving in a circular path, it will always have a centripetal force, some force that's pulling it into that path. And in this case, that is the static frictional force.
So like the weight or centripetal force, gravity wouldn't come into play with any of
No, and the reason that it doesn't is, let me draw a cross section. So this is my car. Here's my car. The static frictional force is, towards the center of the circle, but your normal force is up, and your weight force is down, is not towards the center of the circle at all. That changes if you have something on a banked curve, because then that normal force actually is pushing towards the center of the circle, or at least a component of it is. Then it becomes sort of like the salad spinner at the fireman's fair, that you then have a normal force that's pushing you in the direction of the center of the circle, or the gravitron, or whatever they call it. I can't go on those things anymore. I used to like going on those things, but now they just make me dizzy. Did they make y'all dizzy? Yeah. Dizzy?
Yeah, way beyond.
Way beyond dizzy, okay. All right. Okay, what else? Okay. Yeah. So let's just start. I'm gonna write down the things that we know. My omega is 3 radians per second. I want to know the time that it takes, and my theta is 1 revolution. So first of all, I recognize that I have a mismatch of units here, because I have theta in revolutions and omega in radians. So I need to go ahead and convert this into radians, which fortunately is pretty easy to do. Like 1 revolution is how many radians? 2 pi, or about 6 radians. So now I'm just going to go to my basic definition for angular velocity. That angular velocity is angular displacement over time. That's not a new equation. That is just this equation, theta equals omega t plus 1/2 alpha t squared, but it's assuming that alpha equals 0, and so I'm just left with this, which if I solve for omega, I get this expression. This is just speed is distance over time. That's all that is. Angular speed is angular distance over time. So now I'm looking for the time. So t is equal to theta over omega. Theta is 2 pi over 3. 2 pi is approximately 6. So 6 divided by 3 is about 2. Okay? I know you don't have that. Well, you do have that equation, actually. When you have this one, it's just this is a special case when acceleration is 0. Yeah, you were just, because I don't tell you anything about the acceleration, that's how you know, because if it was accelerating, I would tell you.
So with any other problem, you tell us that we can assume.
Yeah, well, yeah, sure, yeah, you could assume that. If you ever have any question like that on the test, you're welcome to ask me. If you're just not sure, usually I'll just sort of sit there and listen to the words that you say, and sometimes I'll repeat the words back to you, and then usually the student figures out what it says. I'm not going to give you special information, but I can help to clarify what's stated there. Okay? You're welcome to ask me during the exam. That's no trouble at all. Or the quiz or whatever. Okay? We'll look at number 4 while we're here. I'm not saying it's on the quiz, but I just noticed it here. Number 4, I give you the radius is 0.1. Notice I'm just writing down the things that I know. I'll write it up here. So let me just extend this page a little bit. The radius is 0.1. The angular speed is 5 revolutions per second. and I want to know what is the acceleration of this object. I know this is going to be my centripetal acceleration, by the way, because it has a constant angular speed. That means that alpha is equal to 0, so there is no linear acceleration, but there is a centripetal acceleration. You understand the difference in that? That the linear speed of this object is not changing, but the velocity of this object is changing constantly, because it's changing what? It's changing direction constantly. Yeah, if I'm asking for acceleration, sure, yes. All right, so here I'm looking for that centripetal acceleration. But remember that any time that I'm looking for centripetal acceleration, which is either v squared over r, or in this case it's going to be easier to do omega squared r, that I have to have it in radians. I have to have it in SI units. So omega is 5 revolutions per second. 1 revolution is 2 pi radians, so that is 10 pi radians per second. And then I'm noticing that I have pi over here in some of the options, so I'm just going to keep that pi until I get to the end. So then I can figure out what is my centripetal acceleration. It's omega squared, that's 10 pi squared, times the radius, which is 0.1 meters. That's 100 pi squared times 0.1, that's 10 pi squared. So E is the right answer. A lot of units, gymnastics with units that you have to do. Be very careful on looking at your units. They're your friend. All right, what else? I'll just sort of go through here. Did I say it makes me sad that we're not doing chapter 9? I said that already, didn't I? No, let's just do chapter 9 on the exam. How about that? Life is short. We only get to live once. We should just do chapter 9, right? No, you don't. In fact, like if you were to take physics at LSU, they have it in a 3rd course, so it's sort of tacked on to the end. But if you're pre-med, you need to review it, and you will when you study for the MCAT or whatever, the DAT or whatever it is that you're doing. What?
Exam 3, number 14.
What semester? 19. Exam 3, 14. Okay, what semester, Megan, did you say? Fall 19. And what number? 14. This is the number 14 on number 14 on fall 19. Okay, yeah, so this is a lot like that Ferris wheel problem we worked before. Although in this case, he's at the highest point. So my Ferris wheel, I'll just draw the top part. He's right here. I have my forces, my normal force, my weight, like that. So I know the sum of the forces is going to be Fn minus Fw. I know that my acceleration, which is center seeking, is towards the center of the circle, so it's going to be negative. So this is equal to the mass times the centripetal acceleration, but I'm going to go ahead and put a little negative sign right here to make me remember that this is a negative acceleration. And so now I want to know what is the normal force. The normal force then will equal to the force weight minus MAC, and that negative comes about because I know that centripetal acceleration is in the downward direction. That's where that negative came from. The weight is, it's 100 kilograms, so that person weighs 1,000 newtons, minus 100 kilograms times the centripetal acceleration. I'm given omega right here is equal to 0.2 radians per second. So remember, AC is equal to omega squared r. So this is going to be 0.2 squared times the radius, which is 30 meters. Well, I know it has to be less than 1,000, so it gets rid of these. I think it's probably B. Is it B? I'm pretty sure it's B. So that's equal to 880. So just in the process, notice that, I drew this picture. Picture always helps me. Like even now, I've done these a gazillion times. Like I still have to draw the picture and think about it. What is the direction of what are the direction of the forces? What is the direction of the acceleration? And then imagine where I am. And then I still have to write out Newton's second law, and then recognizing the sign that I have here. Also notice that I wrote out what I knew here. I didn't actually do it very well. My radius is 30. My mass is 100, and I was looking for that normal force. Okay, you'll want to do all those steps. Don't skip over those steps, especially on the quiz, because you should have plenty of time for the quiz, and just be rigorous. Make it. The reason is the acceleration is always towards the center. So if it was at the bottom, you're right. It would always point towards the center of the circle. And that would be a positive acceleration and a negative acceleration. There was a similar problem we did in class where you have somebody on a road like this. And this is like the top of the Ferris wheel. This is like the bottom of the Ferris wheel. It's the same situation. It's just a slightly different context. All right? What else? I only have about 5 minutes. I have a student coming. But have other questions? You feel ready for the quiz? Yeah? Okay. All right. Well, let's stop there.